Now in this two cavity klystron, the cathode emits the electron. Okay, you just remember now. Cathode emits the electron. Here is the okay grid. Okay, anode grid. It accelerates the electron to propagate in a axial position. Okay, toward the collector here. Okay, that is about a anode grid. So now when it reaches to the cavity, this one is about a first cavity. This one is a two cavity klystron. So in a first cavity, we are providing the RF input. Why we are providing the RF input? This two cavity klystron is used as a amplifier. Two cavity klystron is used as a amplifier here. So now we are providing the RF input to the cavity. Okay. So now when the signal RF signal is propagating through the cavity, so this one is nothing but a RF signal, and because of this RF signal, so positive RF signal. Okay, because the positive half of a RF signal. Okay, when electron propagating from the cathode in this particular okay positive half cycle of this RF signal, so they move faster there, and those who are propagating in this negative half cycle, they move slower. Okay, slowly. Which here faster the okay electron because of the positive half cycle, negative half cycle. Okay, decelerate. Okay, here it is accelerate here. We can say that is about decelerate, or we can say retardate now. So means here it is a faster one. Your electron is moving faster, and here it is a slower now. And those electron at this okay at the position of this RF signal 0 here. In that case, the electron velocity will be a constant. They will not change their velocity. Only in this positive half cycle they will move faster. In this negative half cycle they will move slower there. And then when it is moving faster and slower, at some particular point they will form the bunches. Okay, now this is the distance. Okay, we can say that is about the optimum distance. Optimum distance between these two cavities. Okay, we can say that is about the optimum distance. Now we can say that here RF signal is there. We say RF signal is there. Is okay. That is about the opening of mouth of this particular cavity, and due to this RF signal, the bunches formation is takes place. Here the bunches of the electrons are propagating through this drift region or a drift space. This one is the cavity distance between these two cavity opening. So that's why we can say that it's about a drift region or a drift space. Now here these bunches have the okay energy. That energy is called as because they have a electron, they have velocity as well as a potential there. Because potential they are getting from what? That is the DC beam voltage. This is about a DC beam we are providing to this okay to this cathode. This is about a DC beam. So with the here this electron bunches okay bunch the electron here, they have the kinetic energy. When they reaches okay they because they have a high velocity now, they will reaches to this catcher cavity. This one is about the catcher cavity. When it reaches to the catcher cavity, that bunches provide their energy or release their energy to this RF field. So once they release their energy to the RF field, your RF output will be increases. Means we will get that RF output what? That is about the amplified output. We'll get that RF output is amplified because that bunches release their energy, that kinetic energy to the catcher cavity. And then once they release their energy, then slowly they okay release the energy, then they slow down. Here they release the energy, so that's why the bunches is slow now. Here it is a faster one. In this drift region, they have the kinetic energy, so that's why they are moving faster in this drift region. But when that reaches to the catcher cavity, these bunches release the energy to this a catcher cavity. Once they provide their energy to the catcher cavity, that velocity reduces. So that's why these bunches slowly move toward the collector. This one is about the collector. Means all the bunches are collected at the collector here. Okay. Now this one is about a drift region, and here we say that this is nothing but a cavity gap. We say that is tuning takes place, or we can say that is about a timing period of what we can say T0. Here we can say that is about a tuning T1. Here we can say that here it is about the gap here. We can say that is about T2. We can say that is about T3. So at T0 what happened? Electrons start accelerating. Okay, once the T1 is completed, electrons start moving faster or slower. Okay, at T2 they start provide the energy, and after T3, they already their bunches releases their energy, okay, to this cavity there. And they collect. Then at the end, they will collect it at the collector there. Now the phenomena of what? Faster the electron. Okay, here we can say that electrons are faster and slower here. The velocity of the electron is increases because they are moving in the positive half cycle or positive half of RF cycle. Okay, this one is about your RF input. When electron moving in a positive RF cycle, they will be faster, means velocity is increases. The electron moving in a negative half cycle, they lower their speed. Okay, velocity will be lower as compared to this electron. And those who are moving, okay, here we are changing the positive and negative half at this particular place. This will have a zero field. Means we can say that electron will be of a constant velocity. Velocity will not change. Now the variation in the velocity of faster electron, slower velocity, constant velocity, that variation in the velocity is called as a velocity modulation. All of you remember that? Why? What is called velocity modulation means what? Here is the variation in the velocity of the electron due to the RF field. So that's why it is called as a velocity modulation. When they reaches, okay, when they reaches here, the bunches formation takes place. Okay, reaches means bunches formation
Sorry,
takes place.
sir. It is
Now
not
these
visible,
bunches
sir.
propagate, okay, these bunches propagate towards the catcher cavity. Now when it reaches to the catcher cavity, what happens? That catcher cavity, okay, when it reaches to the catcher cavity, this electron release their energy, okay, that kinetic energy to this RF field. Means what happen here? They provide the kinetic energy to the RF field. So that's why you can say that that energy given to the RF field. So that's why amplification of that RF signal takes place here. Means what happen here? We can say that energy, kinetic energy is given. Means current induced here. Okay, current induced. That's why we can say that energy release. That is, we can say that is about the current modulation takes place here. Velocity modulation here. Bunches formation takes place due to the RF field. They release the energy, kinetic energy to this cavity. So that's why current modulation. Means two modulation takes place. We can say that a velocity modulation and a current modulation takes place inside this particular two cavity klystron. Now another thing is what here two cavity klystron. We can use a multiple cavity instead of only a two cavity. We can add a multiple cavity here. And then how to add a multiple cavity? We need to do one thing. Okay, what we have to do? We need to do one thing. What we need add a one more cavity. Okay, add a cavity here. We can add a cavity here. Okay, so now this is called as a multi-cavity klystron. So we'll see that multi-cavity klystron later. So we'll finish a two-cavity klystron first, and then we will go ahead with a multi-cavity klystron now. Now, any questions or any doubt, you write a questions or doubt in a chat because sometimes I am not able to hear your voice. You mention if you have any questions or any problem, you write a questions in your chat. I will repeat it again. Okay, no problem. So this one is a concept actually. If you have any question or a doubt, you can speak out. I am able to solve your doubt. Okay. Now we'll go ahead here. Now this is about your cavity now. Okay, this one we can say is about a slower electron and a faster electron. We can say this one is about due to that we can say that a bunches formation takes place here. How actually current model? Okay, because they are providing their energy. Okay, they are providing their kinetic energy to the RF field. Due to the providing the kinetic energy to the RF field, amplification of the RF signal takes place, and that amplification is called as a current modulation here. Okay, or you can say that a amplification of your signal. So that is about, we can say that is about a current modulation takes place. The word we have used, that is about a current modulation. Now we will continue now here. Now I am going to share you the PPT. Okay, PPT, and we'll solve some. We'll see that some of the portion that remaining. Okay, this one is about a bunches takes place here. Okay, this one is about your two cavity klystron now. Now in this two cavity klystron, if you see here, you can see that cathode. This one is about the anode. Okay, so here we can see that about the RF input is providing. This one is about a drift region or drift space. Bunches formation takes place. Okay, and here the bunches releases the energy, and they will collect it at the collector here. Okay, they will be collected at the collector. Now this one is about your, you can say that a two cavity klystron, and then this RF output will be amplified. Now this one, okay, this is a gap. This one is about a buncher cavity. Okay, this one is the buncher cavity, and this one is about a gap. So for this particular gap, we can say that gap is about what? A D here. This one is about a gap is about a D here, we will say. Okay, this one is about a gap, we can say. This one is about a gap. We'll say that gap is called as a D here. And this is a spacing here. Wait now, video. Now this gap is called as a 0 to D. Okay, that's why it's called as 0 to D here. That is about a gap. And here it start, okay, we can say that T0 to T1 time. This one is a time, so that interaction of that electron to this particular field, interaction of the electron in a RF field, that is about a time. And this one is about a T1 to T2. This one is about a time here that bunches of the electron is propagating through this drift region. Then T2 to T3, that is nothing but what? They provide, okay, T2 to T3, they provide their energy to this, okay, cavity, that is called as a catcher cavity. So that's why we'll get that RF output amplified here. Now next is about what? These are the distances, you just remember, 0 to D. This one is about L plus D, actually total distances. That is about the L, we can say length of the cavity here. Okay, this one from this to this. Okay, this is about your length of the cavity. So now a reflex klystron. Okay, so okay, now this is about two cavity klystron actually. Okay, so we can consider that two cavity klystron. Okay, these are nothing but a explanation. Now bunching of electron takes place. This one is about your RF field. Okay, here we can say that is about the RF field. This one is about a positive. At this particular point, electron will move faster. Here, this is about the negative half cycle. Electron will move slower here. And here, that is about the change of state. You can see that at the zero position of this RF field. So here, it is about the same. Velocity will be same. And they will reach at this particular point. It is about the bunching center. Bunches takes place. That is about the distance, you can say, a length here. And this one is about a sinusoidal signal, that is about a RF input. RF input Vs is equal to Vn sin of omega t. Now what happened here? That V1 is small as compared to the V0. Okay, V1 is small as compared to the V0 there. So then because V0 is nothing but a DC beam voltage. Okay, as compared to the V1, V0 is larger. Next, we will consider that. Okay, now you just remember that I'm just going to explain you those expression now. The velocity of an electron entering the buncher cavity, which start entering the cavity there, under the influence of what? High DC voltage V0 can be expressed as V0 is equal to what? That is about a small V0 is equal to under root of twice of E V0 by M, or if you solve it, E and M, okay, ratio of that 2 by E M, under root of it, you will get that 0.593, and that under root of V0. This V0 is a capital V0, that is a DC voltage. That is a DC voltage we apply to the cathode, that is called as a high DC voltage. Okay. Then a gap voltage, means we can say that is about the RF signal. That is about the Vs is equal to what? That is the signal V1 of sin of omega 2 t. Average transit time through the buncher gap distance d, because d is the distance. That is nothing but what? T1 minus T0. T0 is start point, T1 is the end point. So that is about the average transit time of this particular, in between this particular gap. That is a T1 minus T0. So tau is about what? Average transit time is equal to what? That is about the d is nothing but the distance or a spacing in the cavity there, and V0 is nothing but the velocity of the electron. Okay, that this one is a small v, this one is a capital V. The average gap transit angle, that is theta g, is equal to omega tau, approximately omega d by v0, or we can say that omega of t1 minus t0. The average micro voltage in the buncher gap can be expressed. This one is about the micro voltage in the buncher gap. Okay, buncher cavity means what? Where the bunches formation takes place. That is called a buncher cavity. So that is, can be say that average micro voltage in the buncher gap can be expressed as Vs is equal to 1 by tau T0 to by T1 V1 of sine of omega t dt is equal to V1 sine of theta g by 2. This one is about the theta g is nothing but what? Average gap transit time angle by 2. Okay, because we can say that a gap transit angle, okay, gap transit angle from the 0 to d. So at the center itself, okay, we can have a micro, okay, micro signal higher. That's why theta g by 2. V1 of sine of theta g by 2, theta g by 2, sine of omega t0 plus theta g by 2. And this one is about the ratio sine of theta g by 2 by theta g by 2 is called as a beam coupling coefficient. So beta I is equal to what? Sine of theta g by 2 divided by theta g by 2. Okay, that is about a beam coupling coefficient. Beam coupling means what? Where we provide, we get that beam, okay, coupled to the whatever the buncher cavity there. Okay, that is about the gap. This one is about a gap of a cavity where that beam is coupled there. So that's why the bunches formation takes place. So that's why I can say it is about a beam coupling coefficient. So now this is about a gap transit angle, okay, or you can say that is about the beam coupling coefficient, that's about the beta. So if the gap is increases, okay, so beam coupling coefficient decreases here, so we can consider that gap transit angle because of whatever the distance we have. Then at the buncher cavity, the input signal is superimposed on the DC voltage, and hence the velocity of the electron exciting from the buncher cavity will be V of T1 is equal to V0, capital V0, B1. V1 is about your signal, omega T0, that is about the time, okay, and theta g by 2 is about transit angle, and we can solve it. And this is about this called as this factor beta 1 V1 by V0 is the depth of velocity modulation. This V0 is your beam voltage, and this V1 is your input signal. If V1 is a large, so now okay, velocity modulation is different. Okay, V1 should be small. Okay, so we can say that this is about the factor. So this one is about the depth is depending upon that beta, beam coupling coefficient. And this beam coupling coefficient is depending upon that how much is the gap transit angle. So that's why we can say that this particular factor, beam coupling coefficient, as well as the input signal and a V0, we can say that this is called as a depth of a velocity modulation. And if supposed to be V1 is very, very small, we can say that Vi is very less than 1. Therefore, V of T1, if we solve it, V of T1, we'll get that under root of, okay, this one, if just continue here. Okay, this one expression, we just use this expression and we take this common. And this one we have, okay, expression there. So substitute that V0 is equal to under root of twice of E V0. If we solve it, we'll get that V of T1 is equal to V0, 1 plus this factor, okay, depth modulation factor, and sine of omega T0 plus theta g by 2. And that is called as a velocity modulation, or this equation is called as velocity modulation. Or we can alternately we can solve it. V of T1, V0, 1 plus. Here instead of that theta g by 2, here minus, okay, this one is about it, a minus sign. Okay, so why this alternate form? Because of whatever the sign of angle we have considered. Okay, according to that we can find out. Next one, this earlier I told you this diagram, because fast drop electron or a slow of electron is called as the applicate diagram. All of you remember this diagram is called as a applicate diagram. Here the buncher grid, this one is about your RF field, these are about the electron here. Okay, bunching of the electron takes place. This one is the bunching center. Bunching takes place here. And this one, we can say that bunching takes place because of that motion of the electron. Okay, velocity of the electron increase or decrease because of that RF field. So that's why we can say that due to the RF field, Electron, if this RF field is a positive, it will be a faster. RF field will be a negative, it will be slower. Okay, the transition of the RF field is 0 here, so it will be same. Velocity of the electron will be same. So that way we'll get that faster and a slower electron. So now this one is the distance where the bunches formation takes place, bunching center. This one is the distance from the buncher grid or bunching cavity to the distance called as a where we are getting the bunches, that is called as a delta L. Okay, now if you read it, under such circumstances, all the electrons leave the cavity and will arrive at a distance d delta L. Okay, from the buncher cavity at the same time Td and will form the bunches of the electrons. So that's why we can say that delta L is equal to what? Whatever the timing we say that Ta, Tb, Tc, we say Td. Td means time where the bunches takes place. T is what? Where we can say that cavity started here, here Tb. Okay, that is about, we say that is about a transition of the field we have, and Tc is nothing but we can say that is about a where we have a positive cycle of this field. Okay, so this Ta, Tb, Tc, okay, these are the timing duration, and here Td means it takes a time. Okay, it will take a time to form the bunches, so that's why Td time. So delta L is equal to what? Is nothing but whatever the velocity of the electron and Td minus Tb. Okay, because Td is what? Distance, or we can say that time where we have get the particular bunches there, and Tb is nothing but that is about the center form, or we can say that V minimum and V maximum. V minimum means what? Td minus Ta. Here we can say minimum. V max is what? Td minus Tc. That is about the maximum time. Or we can write in alternate form here, this expression. We'll get that V max is equal to what? Is equal to V0 in bracket 1 plus beta I V1 by twice of V0, and V minimum is equal to V0 1 minus beta I V1 by twice of V0. By substituting the expression of dl, we'll get that delta L. Okay, and after solving all these expressions, okay, we'll get that delta L. Okay, you just remember this equation. Delta L is equal to V0. Td is what? Where we are getting the bunches formation takes place, that is the time. And Tb is what? Where your field, that RF field will be a 0 here. Okay, transition of a 0 occur. And this is equal to what? V0 pi of V0 is capital B V0, V voltage, and omega beta is V1. This is nothing but a delta L. And this that timing, okay, we can say that if the Catchery cavity is placed at a distance L, okay, distance L means what? Okay, this one is about the delta L we say. Okay, this is about your distance. If we place the catcher cavity here means what? Directly they will get what we can say that they will get the energy. Okay. Now this one is about a buncher cavity, and this one is about a catcher cavity. Now wherever we that forms a bunch is there, if you put that catcher cavity there, automatically whatever happen, all the energy will release there inside the particular cavity there. Okay, that's why we can say that if the catcher cavity is placed at a distance L from the buncher cavity, then the transit time of the electron can be expressed by what? T2 minus T1. Okay, so we can solve it for this T2 minus T1, means where the D0 is equal to what? L by V0 is the DC transit time. And after solving that, okay, this expression will get that T. And that T is nothing but what? We can say that is about a T2 minus T1. Or we can replace here omega T is equal to omega T2 minus omega T1. And omega T2 means what? That is about the end time. Okay, here we can say the transition start here. So that's why if you solve it, okay, if you continuously solve again the equation there, we'll get that theta 0 is equal to omega T0, omega L by V0 equal to twice pi n. And this x, that is about the bunching parameter of a Klystron. X is equal to what? Beta I V1 by twice of V0 into theta 0. This one is a DC transit angle, and this one is about the bunching parameter. This x is a constant whenever we have that fixed value of that beta I. Okay, so we can say that x will be constant, that is 1.814. And the instant at which the electron will arrive at the catcher cavity, okay, second cavity, when it will arrive at the catcher cavity, so then what happens? T2 is equal to what? T1 minus T1 plus T0 into what? 1 minus dy V1 by 2 is 0. Sin of omega T1 minus theta g by 2. And that is nothing but what? After, if you solve it, omega T2, this one omega T2 minus theta 0 plus theta g by 2. That is about the catcher cavity angle is equal to omega T0 plus theta g by 2 minus x of sin omega T0 plus theta g by 2. Okay, this is about a buncher cavity departure angle. This one is about, we can say that is about the catcher cavity arrival angle. Okay, catcher cavity arrival angle and buncher cavity departure arrival. Buncher cavity departure arrival here, angle here, and a catcher cavity arrival angle. Okay, so this one is about a buncher cavity. Okay, you can say that this one is about a catcher cavity. The x, that factor of ax, where we are getting the bunches takes place. Okay, and then they release the energy to the catcher. So this is the region here we doesn't work. This one is about a region here we will work. Okay. Next we can find out, okay, how much is the current propagate. If we assume that dq0 is the amount of charge passed through the buncher cavity at a time of interval dt0, then dq is equal to what? I0 dt0 is the current. According to the conservation of charges, the same amount of charge will also pass the catcher cavity at a later time of interval dt2. Hence, we can write this expression. Then we can find out, okay, what will be the total current propagating through it. That is at the I2 is that is a current at a catcher cavity. So I2 we can express in terms of what? I0 by what we can say that 1 minus x cos of omega t minus theta 0 minus theta g. That is nothing but a I2 current. And here catcher cavity arrival angle. Okay, and this one is about a normalized beam curve, where we are getting the maximum value. Okay, maximum value of this current. Okay, that catcher cavity arrival angle is used. Now for this expression, if you see that x is equal to 0.05. Now the current will be what? Normalized beam current will be like. Here we can say that x is equal to 1.0. Okay, this one, the catcher arrival angle is 1 now, but the beam current will be increased. Okay, so now this way we can consider that the beam current, okay, bunches are formed at the periodic interval. The beam current in the catcher cavity is also periodic form of a period twice pi by omega. Therefore, the current I2 can be expanded in a Fourier series. And this one is about a Fourier series. And we generally consider that for the I2 value, the fundamental component has its maximum amplitude at x is equal to 1.814. Where we get that 1.814? Here we can say that x 0.5, x 1.0, x 1.5 likewise. So where we are getting that x is equal to 1.814 here some. So that is about it, where minimum catcher angle and the minimum catcher arrival angle will get that x will be higher. And so that at that particular point, current will be a maximum. Means maximum amplitude. Where we are getting maximum amplitude? At x is equal to 1.841. So therefore that x, okay, bunching, okay, we can say that bunching parameter x is equal to what? We can say that beta p1 by twice of p0 into theta 0 is equal to 1.814 here. But when this x is equal, so we need to solve this Fourier expression. If is equal to what? Twice of I0 j1 of x. So that j1 of x, where at n point, where n is equal to 1, 2, 3, 4, and where we are getting that j1 of x, okay, at a maximum. So j1 of x at what? That is about what we can say, that is about the value x is equal to 1.814. So the optimum length, we say L optimum, that is about the length where we are getting that maximum bunches formation takes place. Okay, minimum value we can consider. So that's why optimum length, so is equal to what? 1.841. Or we can find out delta L is where distance or center distance where we are getting the maximum center of the bunches formation. L optimum is what? It is about the optimum distance. Okay, where is a small or approximate value of that particular distance where we are getting that maximum fundamental component of current, and that will give that we will get the more energy. Okay, we can say that amplification. In terms of amplification, we can say that more amplification takes place. So I2 current, induced microwave current in the catcher cavity, is equal to beta 0 into I2 is equal to twice of beta 0 I0 G1 of x and cos of omega t minus tau minus T0. And this beta 0 is called the beam coupling coefficient of the catcher cavity. And then power output. Okay, how much is the output power? Depending upon that, how much is the induced current there. The output delivered to the load and the catcher cavity is given by. This one is about equivalent circuit of a Klystron. We will get that P out is equal to what? Beta I0, that is about the cavity. Okay, sorry. Beta 0 is equal to, we say that beam coupling coefficient of the catcher gap. Okay, and this is about B0. Okay, so that is about the catcher cavity output. I2 is a current, output current. So that is nothing but P out is equal to what? Beta 0 of I2 square into RSH by 2. We will get that P out likewise. And according to that, we can find out the efficiency of the Klystron. Efficiency of the Klystron is what? P out by P in. How much is the P out? That is about a P out at the catcher cavity. P in means what? At the whatever the beam signal we have. Okay, input signal, beam current. So that's why twice of I0, B0 is. That is about, you can say that a electron, or you can say that efficiency. So we can obtain that. What will be the maximum electronic efficiency or a maximum beam current? If the coupling is perfect, okay, we can say that beam coupling, we can say it is perfect, or we can say that catcher cavity is perfect. In that case, we say that beta 0 is equal to 1, V2 is equal to V0, means output V2 is nothing but a V0, that is maximum beam current approaches. So I2 max is equal to what? 1.164 of I0. So maximum electronic efficiency is what? Beta B0 I2 to V2 by twice of I0 V2. If you put that, okay, whatever the I2 max here, we'll get that efficiency of 0.58. Maximum electronic efficiency. The practical efficiency of the Klystron is about 15 to 30%. Okay, if you see that here, efficiency is not 50%. It is less than that. And we should know that what will be the gain. Okay, what will be the gain of a Klystron there? So that is nothing but a voltage gain. To obtain the voltage gain of a Klystron, we need to consider that where we are getting the maximum output. So that's why the gain is equal to what? V2 by V1. Generally, V2 is what? Beta 0 I2 RSH by V1. We can put that V2, okay, here. And we can express that V2 in terms of whatever the equivalent visual conductance of a Klystron amplifier. That is ratio of what? Gm by G0 is equal to what? This one, G1 of X. If you consider that G1 of X at what? X is equal to 1.841. We will get that Gm by G0, that ratio, is nothing but 0.316 beta 0, theta 0. Okay. So you will get that G available voltage gain here in this particular expression here. Okay. Or you can say that current induced in terms of this. So now the bunching parameter and the normalized transconductance. Now if we consider that here, transconductance value, that is, we can say beta 0 and theta 0 factor, depending upon that, whatever the bunching factor and whatever the transit angle. So this way it is bunching parameter takes place. Okay, and we will say that whatever based on bunching parameter, we will get the normalized transconductor, so that output reduces or output increases. Then we can find out, substitute that Gm by G0 in the expression of the voltage gain. AV is equal to what? Gm by G0, G0 into RSS. Gm, okay, we can have the gain there. And this is about your output, okay, impedance. We can consider that power required to produce the bunching can be expressed, this one, expression of the power. Or we can say that power required to produce the bunching can be also expressed in terms of a bunching conductance. So PB here, and this ratio GB by G0. And this is nothing but a DC power required to produce the electron beam. Here we can say that is about the gap, transit gap angle. And here we can say that is normalized electronic conductance. if that theta g, okay, so that's about it. Transit gap, yeah, we can say that the gap angle here changes, okay, so we can say that a normalized electronic conductance is increases. Okay, that is about your two cavity crystal. If you use or we can say that coupling the another cavities, okay, in that case we can multiple or we can couple the multiple cavities there. Now the output of this particular cavity, okay, output is dependent upon average energy of the electron leaving the Buncher cavity over a complete cycle is almost equal to the average energy of the electron entering the cavity during the period, provided the Buncher cavity gap is negligible here. If the gap is not negligible, then the average energy of the electron leaving the Buncher cavity over a cycle is larger than the energy of the electrons entering the cavity during the period. So that's why we are getting that difference in the energy, okay, or differences in the whatever the output now. So that's why we can consider that the two cavity can be used in a wide application. We can say that throughput scatter transmitter, UHF transmitter, power amplifier, and in a ground station for the satellite communication. That is about a two cavity Klystron. Next is about a multi cavity Klystron. In a multi cavity Klystron, what happens? The cavity instead of a two cavity, there will be a multiple cavity. But these cavities are cascaded number of cavities to achieve the enhanced gain. Okay, to increase the gain, we have to use a multiple cavity here. See here. So these are, if you consider that two cavity Klystron, Buncher cavity and a catcher cavity. But in a multi cavity Klystron, there may be an intermediate cavity, and that intermediate cavities are placed in such a way that we'll get that a maximum output. So now earlier we say that we need to consider that delta L in between that what Buncher and a catcher. Now here this intermediate cavity is used to provide the energy to the bunches, or they are used to form the bunches there. Okay, means that cavity. Energy as well as the bunches formation. They help to the formation of a bunches. They help to provide the energy to this particular bunches. Now this is about the use of this particular intermediate cavity. And these are the magnetic coils because electron will move at any position there. So these magnetic coils are used to focus all the electron in the given direction. That is about the beam here. Okay, in this particular beam, they will focus. The same principle is same. This one is the Buncher cavity. Bunches formation takes place. They are energized here by this particular energy of the cavity, energized here. Bunches form, and now here the catcher cavity, they will release the energy inside this particular catcher. But due to the addition of this particular cavity, the gain will be increases, output will be increases. Okay, so that's why we can say that to achieve the enhanced gain, so we can use a multiplier. But again, the what intermediate cavity act as a buncher and are placed at the distance of the bunching parameter x 1.84 from the previous cavity. Or generally what happens? This cavity distance gradually decreases. So this to this, suppose I am saying it is a 2. From this to this, it will be 1.5. From this to this, it is about 1. So gradually, the distances decreases here. So that we'll get that a maximum output. Here the decreasing in the spacing between the consecutive cavities. So means when that x is equal to 1.841, okay, when we are expecting that x is equal to 1.814, that is about the distance between the cavity there. In that case, it is depending upon that bunching parameter. So at what point we are getting a 1 point? So we need to place the cavity, or we can say that in the decreasing spacing, okay, in the decreasing the spacing between the consecutive cavity, so that we'll get that x is equal to 1.841. If we want to keep the intercavity distance constant, then to maintain x 1.841 and the beam voltage is difficult. Okay, we could not maintain x 1.841. In that case, we can increase the beam voltage. Okay, must be increased in the consecutive cavity. So that is about a multi-cavity Klystron. Okay, multi-cavity Klystron is used at a higher operation. Beam is large, therefore the mutual repulsion cannot be neglected here. The space charge force within the electron bunch depends on the size and shape of the electron beam, because there the cavity is too large. For an infinite beam, the axial component is less as compared to the infinite beam. Due to the reduced axial phase charge force, the plasma frequency is reduced and plasma wavelength is increased here. Okay, due to reduced axial phase charge region, this one we can say that is about it. This one is about a space charge, space region. Okay, drift space region. And then we can consider that we use both the things, and we assume that both the charge density and velocity perturbation variations are in this particular cavity. So these are the expressions here